say we were given the limit as x approaches 0 of e to the x minus 1 divided by x, right? So when we try to plug in the 0, we get e to the 0, which is 1. So we get 1 minus 1, 0. And then 0 is, well, 0. So we end up with that 0 divided by 0 form. So it's safe to use L'Hopital's rule here. So if we try doing, or when we use L'Hopital's rule, we take the derivative of this upper function, e to the x becomes e to the x. Negative 1 is 0, it's just a constant. So we end up with e to the x, and the limit as x approaches 0, right? And then the derivative of x, that's going to be 1, so we're just going to divide by 1 here. So when we plug in the x again into this new limit, well, that's going to be e to the 0, which is 1, divided by 1, so the answer is just going to be 1, right? So that's how we apply L'Hopital's, either when we have a 0 divided by 0 case, or if we have an infinity divided by infinity case. Wait, I don't know why I pointed it here. There's no infinity divided by. Can you record, Courtney? Oh, you did. What a genius. Thank you.
You just look like a clown right now.
I did. Okay.
Yeah, that's our recording.
So then, now let's move on to the good old derivatives, right?
Oh, yeah.
Actually, no, before we do that, there's one last thing that involves limits, and that's for continuity, right? So we can have 3 cases where a function is not continuous. We can have a case where it just like goes like that, there's a sudden hold, and it keeps on going. We could have the case where it looks like it's going to go one direction, then all of a sudden it jumps to another place, and then we have that. Or we can have an asymptote where it's just never going to reach that x value in the first place, so we end up with something like that, right? So this type of discontinuity right here, it's called a removable discontinuity. This type of discontinuity is called a jump discontinuity, right? It makes sense. You can you're kind of removing the point, whether it's defined somewhere else or not, you're removing that point, right? Here, you're jumping from one place to another, and this is very aptly known to be an asymptotic discontinuity. I wonder why. I never understood that one. You guys are supposed to laugh at that. So, if you look at what happens when a function isn't continuous, right? And actually, let me define this to be something over here. What it looks like is going to happen, so say this is at like y equals 8, doesn't matter, right? That point looks like it should have been at y equals 8, right? So as you're tracing out the function, you see that all of a sudden it's not defined here, right? So that kind of the definition for continuous that we've discovered in pre-cal is that, oh, you can't draw without picking up your pen, right? But here you can see that, yeah, you have to actually pick up your pen when you're drawing it, so we can visually see that there's discontinuity. But if we have something that is continuous, right, and I just draw that, and if you think about it just mathematically, the way that the function is moving, right? So you see that at every single point, the function is gonna kind of approach what it's actually, what it feels like it's gonna approach, right? So here, it's approaching this value, and it actually is defined to be the y, whatever that is there. It's approaching right here, and then over here we see that it actually is at that y value. It's approaching this right here, and we see that it's actually at that y value. So what this is kind of telling us is that, well, if we take the limit as x approaches some number of a function, for this function to be continuous, well, at that number, the function also has to equal what it's defined to be at that x, right? So, and that kind of fits our intuitive sense of continuity because, well, the limit is telling us what the function looks like it's gonna do, and the function value tells us what the function actually does. So if it actually does what it looks like it's gonna do, well, that's when we result in continuity, right? So we see over here, it looks like it's gonna go over here, but then all of a sudden it's actually over here, that's not continuous. It looks like it's gonna go over here, but then all of a sudden it's down here, it's not continuous. It looks like it's gonna go to infinity, but then it's not even defined at this x, so it's not continuous. Right, so a type of problem that would ask you about continuity is one of these that I am trying to fill the time with as I erase. Thank you, Corey. So say they gave us a function f of x is equal to, so it's gonna, usually they give you piecewise functions whenever they're asking for continuity, right? So we're gonna be, the function is gonna be x squared plus 1 if our x is less than 0. It's gonna be defined to be 1 at x equals 0. And it's gonna be x cubed plus 1 if it's if x is greater than 0, right? So just looking at this piecewise function, yes, sure.
Okay, guys, think about this. Thank you. I don't want to be cold, so you can. Okay, guys, think about this, and then let's finish.
Oh, wait. Oh no, but no, it's okay. So no, it's okay. It's okay. No, shoot, I'll take it. But no, but then I'm gonna be talking. No. Okay. Thank you, Miss Cool. It won't get cold. Don't worry. I'll eat it between now and after school. So, if we just look at the definition of continuity, right? So the limit as, oh, and by the way, with a piecewise function, we see that this is going to be continuous for all x's that it's defined for. This is going to be continuous and this is going to be continuous, right? So the only possible place where we can't have discontinuity is when the function changes, right? And that's, usually it's going to be a jump discontinuity, right? When we have this, the function is one thing, but then it turns into something else over here. And we see that continuity happen, discontinuity happens. So we're going to try the place where that can happen, which is going to be x equals 0. So limit as x approaches 0 of f of x has to be equal to f of 0, right? So the f of 0 part, that's really easy. The function is literally defined to be 1 at f of 0. So that's 1 over here. But then for the limit part, that's a little bit more tricky, right? Because we see that the function is something when it's to the left of this x and something else when it's to the right of it. So we're going to have to try the left side limit and the right side limit. So when we try the left side limit, we get the limit as x approaches 0 from the left of f of x. And what f of x is on the left, well, that's going to be x squared plus 1, right? And because we're just looking at the left side now, we don't actually have to take this into account. So this is really simple now. We just plug in the 0 because we see that there's no algebra problem. So 0 squared plus 1, that's going to equal 1, right? So we have that 1, and then we have to see, right? We don't know for sure. Question mark equal. We have to see if the limit from the right side is going to be equal to this, right? So the limit is x approaches 0 from the right side of f of x. And if we look at the that's not a plus. That's an x. So if we look at the definition of f over here, right? When it's to the right, we're going to have x cubed plus 1. So we write the x cubed plus 1. When we plug in that 0, we don't actually have to care about whether it's to the right or to the left anymore. When we plug in that 0, we get 0 cubed plus 1, so that's going to be equal to 1. So we actually do see that 1 is equal to 1. So the limit itself is going to equal 1. And we do see that the function value is equal to the limit. So therefore, at x equals 0, we can say that this function is continuous. So if the question we're asking, prove that this function is continuous at x equals 0, well, you'd write f of x is continuous at x equals 0 because the limit is equal to the function, and you show all your work, and you'd have a lot of fun doing your awesome math problem. So now we can finally move on to derivatives, right? So kind of the really most fundamental thing about a derivative is the instantaneous rate of change, right? So usually when we do algebra stuff and we want to find the slope, right? Well, if we just look at a function like this, right? So if we want to find the slope, well, we have that super nice formula of m equals y2 minus y1 divided by x2 minus x1. So the y2 and the x2 are going to be one set of points, and the x1 and the y1 are going to be a certain set of points, right? Or a point. So if we just start over here at, let's say this point, right? So we say this to be the point x, and obviously the function value at this point, that's going to be f of x, right? Because if this is the function f of x, well, plug in x, you're going to get f of x. And then let's say we just move a distance h, right? Well, then over here, we would have x plus h, right? Because if you move h to the right, you're going to add h, right, to take that point into account. And then over here, plugging in that new x value, we get f of x plus h. Right. And so just using our slope formula, well, it's going to be y2 minus y1, so the second y minus the first y. So that's going to be f of x plus h minus f of x divided by x2 minus x1, right? So x2 is our second x, and x1 is our first x. So that's going to be x plus h minus x. You see that we have a positive x and a negative x over here that can cancel. So we're actually just going to be left with h. And so this should look really familiar to you, that this is the form of the whole definition of a derivative, right? But this in itself isn't a derivative because we're missing that very crucial limit, right? And so what the derivative actually does to this is that it makes the distance between this point and this point get really small, right? So right now, the slope that we're approximating is the slope of this secant line, right? It's not that good at drawing, but it gets better, yeah. And then if we move closer and we make h get smaller, well, then we're going to get a better approximation, right? And if we make h get smaller, we're going to get an even better approximation, up to the point where h is basically 0 and we get the perfect tangent line, right? And so if we do take the limit as that distance, or just h approaches 0, well, then that's going to be the derivative. So that's where the whole form of a derivative comes from. And it's completely arbitrary that we chose x over here. We could have also chosen some random number a, right? So we have a and then a plus h, and then this would turn into f of a, this would turn into f of a plus h. And then this is where the second definition of the derivative comes from, where instead of just plugging in a certain x value, well, we're going to plug in a certain number already, right? So we get the that second definition. And we can also just have a point where we have the a over here, but instead of going a distance h, we don't care about that distance anymore, and we're just going to call this second point x, right? And so plugging it into this, we end up with f of this second y minus f of, or that is the second y, and f of a is going to be the first y, kind of writing science, divided by the second x minus the first x, which is going to be x minus a, right? And then over here, well, we don't have a distance that we can take into account anymore, so we will just have to make the x get closer and closer to a by taking the limit as x approaches a, right? So these are the two, well, technically three, right? Because this is just, we'll replace a with x and you get the third one. These are the technically three different forms for the definition of a derivative, right? And sometimes they can actually give you limits that are, like you can't really solve them until you notice that they're actually something that really strongly resembles the definition of a derivative, right? So if we have something like this, the limit as h approaches 0 of square root of 4 plus k, or sorry, I don't know where I got that k from, h, that's the thing we're looking at right now, minus 2 divided by h, right? So I would have no idea how to do this. Maybe we could try the conjugate, but that's going to be too much work because I already know the right way to do this, right? And so when we notice the formatting of this, we see that there's a function with something plus h, and whenever we see h already, we think of a derivative, right? But they could actually be tricky with you and make this be another variable, so don't just rely on that h. But we do see that it's a function with something plus a variable, and then minus something else, and then divided by that same variable, right? And that's roughly what the format of the definition of a derivative that it takes, right? So if you get the limit as x approaches a of f of a plus h minus f of a divided by h, well, we can see that f, well, that's just kind of becoming the square root over here, right? And so we can recognize that our a is going to be 4, and our h is, that's just going to be h. So let's write that off here to the side. A is going to be 4, and we can kind of recognize that the f is going to be the square root, right? So f of x is equal to the square root of x. And then, so now we know that that's going to be f prime of a, right? That's what this comes down to. It's a definition of a derivative, so obviously we're going to get the derivative out of it. And so this question is basically asking us, well, what is f prime of a? Well, our a is 4, our f is square root of x, so let's find f prime of x first, right? So f prime of x is going to be the derivative of x squared. Well, we can kind of, the square root of x. So we can kind of write this in power form to make the whole power rule thing easier, right? So when you do the derivative of this, you're going to subtract 1 and then multiply by that original power. So you end up with 1/2. And then this gives you negative 1/2. So that's going to be the square root, but in the denominator, right? So that's going to be our derivative of the function. But then we plug in that a, right? So if we do f of 4, that's going to be this with the 4 inputted. Square root of 4 is 2. 1 over 2 times 2 is going to be 1 over 4. So this just comes back to you being able to recognize that it's actually a derivative in disguise and not just some tricky limit problem, right? Yes. Okay. So we kind of, I'm already assuming that you know derivatives, obviously, because you've already taken the course, but let's go over the derivative rules, right? So say we had the derivative of a polynomial, right? X to the n, where n is just any number, right? Well, you guys already know that we're going to bring this over to the side and then subtract 1. So we're going to multiply by that n, and then we're gonna subtract 1 from the power, right? So that's just kind of like the definition of the derivative of a polynomial. So power rule, you're all very much used to it. Well, this only really applies when you just have one function, right? But what happens if you have some combination of two functions, right? So say you had a function being multiplied by another function, right? So we have f of x and then g of x. Well, you guys already know what this is going to be. This is going to be about the product rule, right? And if you remember the product rule, that's going to be f prime of x times g of x plus f of x times g prime of x. And obviously there is a proof for this because we wouldn't just do math because we trust that it's right. But it's a kind of a really long proof that has to do with the definition of a derivative. So if you want to look that up, that'd be really cool. But kind of the way to memorize this a little bit easier is that you see that like even if you had 10 functions, what you would do is that you take the derivative of the first function and then multiply all the other functions, and then the derivative of the second function, multiply all the other functions, the derivative of the third function, do that to all the functions, and that's how you see that the little pattern with the prime goes on through the functions from left to right, right? So we could also have another combination, which is going to be the derivative of a function divided by another function. And so what happens here is that we use that little song that Ms. Gould taught us and has been extremely helpful up until right now, and will continue to be helpful. So we have the low, low, low,
Low
D high, minus high,
low. Merrily, merrily, merrily. Divide by low.
Yeah. And so actually, so if you guys already kind of trust that the product rule is correct and like you're seeing the proof and all that, well actually where the quotient rule comes from is actually directly from the product rule, right? So if we have and the chain rule too. Oh wait, what's the chain rule? We haven't even gone over that, right? So the chain rule is what we get whenever we have a composite function, which basically means fancy word for saying a function inside another function, right? So we know this to be the derivative of the outside function with that exact same input, right? So f prime of g of x times the derivative of that inside function. So that's going to be g prime of x. So that's the chain rule, right? So if you apply both the product rule and the chain rule to derive this, what actually happens is that you get g of x to the negative 1 power, and so you do the chain rule over there when you do the g prime, and it just becomes that huge thing. So that's actually where the quotient rule comes from, and you'll see that in any proof that you look up for it if you do, take the time to be a nerd like me and look it up.
It's a flex.
Okay, so now that we know how to take the derivatives, just using those simple rules, let's actually look at some specific function derivatives, right? So say we have the derivative of sine of x, right? Well, you already took this class, so you know the answer, but I'm assuming that like you don't, even though you do. So we know this to be cosine of x, right? And then if we do that for cosine of x, well, we know that to be negative sine of x. If we do that for negative sine of x, well, you know that to be negative cosine of x, right? And if you do that for negative cosine of x, well, you know that to be sine of x. And if we keep on going with this pattern, right, and we do sine of x over here, take the derivative of that, you get cosine of x. You see that it just goes from sine of x going to cosine of x, to negative sine of x, to negative cosine of x, and then loops back, right? So we're going to have that whole sine, cosine, negative cosine, and then looping back. So that's the rule for derivatives. For sine, it's that, right? And then for tangent, secant, cotangent, cosecant, well, we can use that little rule that Ms. Gould taught us, right? And so this is telling us that, well, say we're taking the derivative of tangent, well, we're going to go this way and have secant times secant. So what that's telling us is that the derivative of tangent is going to equal secant squared x, right? I guess this is where we cut off the first part. Yeah. And I'll be here after school to finish the second part, and I'll also finish the second part tomorrow on Friday from 3 to 4. Oh, 5. So Cordy, you can pause the video.
Yes, sir.
Are you going to stay after school?